Hi everybody, welcome to my channel Rahu's Concepts of Physics, Learning the Unlearned. So today I'm going to explain few concepts related to semiconductors, in which mainly I'm focusing on conduction mechanism in n-type semiconductors. So before coming to that, we all know that the classification of material based on band gap can be classified into conductors and semiconductors and insulators. So coming to conductors, there will be a overlapping of bands, conduction and valency band, and because of which the Fermi energy level lies in the valency band. And the examples are like silver, copper, and arum. Coming to semiconductors, so there will be a small energy gap between the conduction band and valency band. So there is a lower band gap between the bands, and Fermi energy level lies in between the conduction and valency bands. And the well-known examples for these semiconductors are silicon and germanium, and you will find a lot of compound semiconductors within this category. And coming to insulators, so in case of insulator, the conduction band and valency band both are separated by a large band gap, and because of which you will have a less conduction in case of insulators. And even in this case also you will have a Fermi energy level in between the conduction and valency band. You will find a lot of examples for these insulators, and few I have given here: plastic and paper. And now coming to the band diagram of n-type semiconductors. So, and here I have given a comparison between intrinsic semiconductors and n-type semiconductors. So here this is the conduction band, this is the valency band in case of intrinsic semiconductors, and this is the conduction band and valency band in case of n-type semiconductors. So in both the cases you are having this similar band diagram, except a additional donor state is present in case of n-type semiconductors. So the main question is how this donor state is arising in case of n-type semiconductors. So as we all know that the best example to understand n-type semiconductors is pentavalent doping of silicon. Suppose you take silicon and you dope with any pentavalent element like phosphorus. So if you dope with phosphorus, you will have a phosphorus is having 5 valency electron. Out of 5 valency electron, 4 electrons will be shared in form a covalent bond with the silicon, and the remaining 1 electron, it will lie in the vicinity of these bonds, and all these electrons will almost free from the other fields and form a separate state in case of n-type semiconductor, which is nothing but your donor state. So presence of this donor state will dramatically influence the conduction or electrical conduction in n-type semiconductors. So because if you take in normal semiconductors like intrinsic semiconductors, so here you have electrons are occupied in valency band, and you need to have a more energy to jump from valency band to the conduction band, so which is not happening at room temperature. But if you coming to the n-type semiconductors, so because of presence of this donor state, you are having few electrons which are sitting in this donor state. If you compare, this energy gap is much smaller than this energy gap, so that the small amount of energy is required to jump electrons from this to conduction band, and in more or less this energy is almost close to the room temperature energy, which is coming from the KBT, right, KBT, thermal energy, which is sufficient to excite these electrons which are present in donor state to the conduction band. So that's where n-type semiconductors are very important in terms of electrical properties. And we can go here more clearly we can explain how the conduction is happening in case of n-type semiconductors. So here the same diagram I represented more elaborately here. So this is the conduction band here, and this is the valency band. So valency band is occupied by the electrons and conduction band is empty. And as discussed earlier, electrons are present in donor state, and mainly these electrons are coming from the foreign elements like phosphorus or any pentavalent element. So, and these electrons are not bonded with any other electrons in the crystal structure, so they are almost free, and they need very less amount of energy to jump from here to conduction band. And coming to this, when a temperature is equal to 0 Kelvin, that means when I am not giving any thermal energy, so nothing will happen. That means no electrons will jump from either valency band to conduction band or donor state to conduction band. So whenever I am giving a small amount of thermal energy, because that energy is sufficient to jump these electrons present in donor state to conduction band, so they will start moving from donor state to conduction band. So when I am giving small amount of thermal energy, these electrons will slowly move from the conduction band to donor state to conduction band. Now if I increase this temperature further 0 Kelvin, so the electrons which are present in valency band, they will start moving to conduction band. And here one important point we can clearly understood from this diagram is, when the electrons which are present in this donor state, when they are jumping into conduction band, you are not seeing any formation of holes in this donor state. Whereas the electrons which are moving from valency band to conduction band, they are leaving a hole corresponding to that electron in valency band. So this is mainly because of the bonding present between the electrons. So as I mentioned in previous, whatever the electrons present in this donor state, all these electrons are free electrons. So suppose I am doping pentavalent element in silicon, so 4 valency electrons are making covalent bond with silicon, and the excess 1 electron which is not bonded to any other electron, and those electrons are sitting in this donor state. As they are not participating in any bonding, when they are moving from donor state to conduction band, so they are not forming any holes in donor state. But in the case of valency band, whatever the electrons present in this valency band, all are in bonding with the other electrons. So whenever you give excess thermal energy, they will break that bond and move to conduction band. When any electron is breaking its bond, it will leave a hole. So that is the reason mainly the electrons which are moving from donor state to conduction band will never leave a hole in donor state, but which is not in the case of the electrons moving from valency band to conduction band. So this is where the main uniqueness of n-type semiconductors will come into picture, and which will dramatically influence the electrical properties of these materials. So thanks you for your attention. Hope you all like my video, and please subscribe my channel and hit the notification bell for any updates. Thank you.